So we are starting a new chapter, chapter 6. Chapter 6 and 7 will come for midterm 3. So chapter 5, we discussed energy, right? So now we're going to introduce something new, momentum. So that is where is my all right. I like the blue. So momentum and collision. So it matters very much, this concept of momentum in collisions problem, crash. So that's why the title is momentum and collisions. So the contents of this chapter, we have only 4 topics, so it's a rather short chapter. We will start by defining what momentum is. Then also come with that is the impulse. So we'll define what momentum and what impulse is. Then we'll find out that the momentum has a property which is the conservation of momentum, like conservation of energy. For an isolated system, this momentum is a conserved property. It doesn't change with time for an isolated system. Then we will look at collisions. Okay, so in collision, we can apply this principle of conservation of momentum, and we will see how we can do that. We'll start with one-dimensional collision first, then we will move to two-dimensional collision. Glancing collisions are where the collision, if you have 2 balls striking, after the collision, they can move different directions, so it becomes a two-dimensional problem. This one is omitted, so it has become even shorter. We will not look at the rocket propulsion. Right. So to introduce this subject, we will talk about collisions. So the conservation of momentum principle that we develop will allow us to solve complex collision problems easily. We don't even need to know about all the forces acting on it. We can use these conservation of momentum principles to solve these complex collision problem without much difficulty. Will also give us an indication of how much force is there in the collision problem, average value for the force. So let's start with momentum. So we will going to define chapter 6. We are going to define what is momentum. So we use the symbol P for momentum, although the first letter of momentum is M, right? But we don't use M, but we use P because M is usually mass, right? So we don't want to avoid it. So P is the symbol we use for momentum. And it's defined simply as mass multiplied by velocity. Velocity, not speed, okay? So since velocity is a vector, now please. No, the way you are sitting, you're blocking anyone coming from inside. You kept the chair like that. So momentum is mass into velocity. Velocity is a vector that will make momentum also a vector. It will have the same direction as the velocity. Mass is always a positive quantity, so it is not going to flip the direction as well. So it's a scalar. It is not going to change the direction because it is always positive. So momentum will have the same direction as the direction of the velocity. What about the units? Mass is kilogram, velocity is meter per second, so its unit, SI unit will be kilogram meter per second. Good. The SI unit for momentum is kilogram meter per second. Do we have a single name for that? No. Okay, like for example, Newton is actually kilogram meter per second squared. But for this, we don't have an official name. We have to say the whole thing, kilogram per meter per second. Right. So, it's a vector. So when you deal with two-dimensional problem, we have to look at the x component of the momentum and the y component of the momentum. So px, the x component of momentum, will be mass multiplied by x component of the velocity. And py will be mass multiplied by the y component of the velocity. Okay. Now we can also see that momentum is m into v, and kinetic energy, if you remember that, what is the kinetic energy? Half mv squared. So we can relate these two guys, the momentum, which is mv, and the kinetic energy, which is half mv squared. It's very simple. Start with the momentum. P is equal to mv. Let's say the magnitude of the momentum will be m into speed. Okay, now the p here is the magnitude of the momentum, not the vector. So square this guy. If you square both sides, you are not changing the equation. So p squared will be m squared v squared. Okay, that we can do. We are not changing the equation. It's still correct. Then you divide both sides by 2 times m. We can do that, right? Same operation both sides. We are not changing the equation. So what this become what? 1m cancel with an m here. And we have a 1/2 mv squared. What do you get? Kinetic energy. So kinetic energy is equal to p squared over 2m. We have proved it. Okay. It's nice to prove something like that, but still, even if you don't bother to do it, doesn't matter. It will be in the formula sheet. Yeah.
How the lower m cancel 2m with the m.
Yeah, this is the m squared, right? This is the m. So 1m cancel with an m here. So the half didn't cancel, it's still there. And m is squared. Okay. Yeah, it's still there. I didn't cancel that. Okay. So I proved it to you. This magnitude of the momentum square divided by 2m is equal to kinetic energy. So if you know the kinetic energy and the mass, we can find the momentum. On the other hand, if you know the momentum and the mass, we can find the kinetic energy. Right. So now that is fine. Now you have to remember there is something called momentum, and its definition is mass into velocity. Momentum is mass into velocity. So if we you have to remember this, okay? Like you remember the kinetic energy half mv squared, remember momentum. If someone asks you what is momentum, you don't have to explain anything. Simple. You ask me what is momentum. If we have an object of mass m, it has a velocity v, the momentum is equal to the product mass into velocity. That's it. Nothing more to tell about it, okay? Like the kinetic energy. Right, now we are going to define another thing called the impulse. So that's the title of this impulse. To come to that point, to define the impulse, let's look at a force applied on an object. What happens to the object? Its velocity will change, right? If you say, for example, a ball is coming, if you hit it with a bat, its velocity will change. That means its momentum will change. When the velocity changes, momentum will change. So let me look at, we can say in order to change the momentum of an object, a force must be applied. Force will change the velocity, therefore the momentum will change. So let me take this change in the momentum, the time rate of change of momentum. Because change in the momentum divided by the time is the time rate, the rate at which the momentum is changing with time. So change divided by the time it takes, it will be the time rate of change of momentum. And P is mass multiplied by velocity. So delta P will be final momentum minus initial momentum. And m is the common factor. I can take it out. So it becomes mass multiplied by change in the velocity. So change in the velocity divided by the time. Do you recognize this guy? It is the definition of acceleration. Acceleration is delta v by delta t. So then I can write it like this. Instead of delta v by delta t, I will write the acceleration. Then when you see this guy, mass into acceleration, you should remember the Newton's second law. What is Newton's second law? Net force is equal to mass into acceleration. So instead of this, I can write the net force. The same. So now what we arrive at finally is the rate of change of momentum is equal to the net force. This is actually Newton's second law. It's nothing but Newton's second law, but expressed in an alternative form. 3 formulas? Now, so far, I have got you 2 definitions. The definition for momentum, which is mass into velocity. Please remember it, okay? Don't worry if you forget it. It will be in the formula sheet, but at least make an effort to remember. Then, this is not something new. This is another way of writing the Newton's second law. So if you want to call it another equation, fine, okay? Net force is equal to rate of change of momentum. But I'm still coming to another thing, which is called the impulse, okay? I'm not there yet, but this is a kind of on my way to introduce the impulse. So we get this one, which tells us net force is equal to rate of change of momentum. This I can say is another alternative statement of the Newton's second law. This is how you see it first, right? Net force is equal to mass into acceleration, which can also be written as net force is equal to rate of change of momentum. The velocity, the acceleration is inside that. Yeah. P is the momentum. So delta P means final momentum minus initial momentum. The change in the momentum. Delta means change.
Minus of y.
This is divide. And this is equal. Minus? No, I'm taking something else. He asked me what is delta P. So I said delta P is final momentum minus initial momentum. Right? You don't only listen to that, it's the whole thing. Okay, all right. I was wondering, did I say something like that? No, I did not. Okay, right. So gives an alternative. No, this one is like it's a Newton's second law, but put it in a different way. Net force not equal to mass into acceleration, but net force is equal to change in the momentum divided by the time. Okay. So even when the force is not constant, whatever the force at that particular time is equal to how fast the momentum is changing at that particular time. So that will be the force. Right. Now, I will continue with that. So we saw the Newton's second law appearing in another way. Now I'm going to define something called an impulse. So the first definition was the momentum. Now I'm going to define something called impulse. Impulse is defined for a force. First, I will start with a single constant force, F. If it acts on an object like hitting a ball with a bat, for a certain period of time, because the ball and the bat is in contact not for long, right? Maybe fraction of a second, then the ball will leave the bat. So we say there is an impulse from this force on this object, and it is equal to the force multiplied by the duration of the force on that object. Okay, it's a finite duration. Maybe when you're hitting a ball with a bat, it may be maybe less than a second, 0.1 second or something like that, because that's a very big force, but acting for a short period of time. So we call this product of the force with the duration of the force as the impulse. And the symbol we use is the first letter of the word impulse, I. Some textbook use J, but our textbook, they use I, so we'll stick to that. So the impulse is equal to the force multiplied by the duration of the force. Yeah, yeah. That we have only 26 letters in the alphabet. Sometimes you have to use the same it over and over again. Can't help. Okay, but you have to know it from the context. No. Don't think about what is the question, what is going to ask. Now let's understand the concept. I cannot do that. Okay. First, yeah, I know where you are coming. You want to know what the question. How do I answer the question? Then, there is nothing. We don't ask anything. Here, there is. Yes, later on we will have, but don't think about that now. Yeah, try to concentrate and learn the lesson, okay? This is the whole thing messing you up, okay? Now don't think about questions now. How can I ask a question before we understand the concept? Right. So the impulse, I'm sorry, Zaid, okay? I need to silence you now. So focus on this material, the concept. So impulse of a force which act on an object for a duration delta t will be the product of force multiplied by the duration. Right. Now you must be wondering, why am I telling all this? You have to wait. I cannot tell everything at once. So you have to be patient. Okay, so we have a reason for doing that. Okay, we don't just do it for the sake of doing it. Okay, so, right. Now look at this impulse. The unit for this. Force is in Newton. Time is in second. So the SI unit will be Newton second. All right, good. But the Newton is actually, in terms of the basic unit, it is kilogram acceleration meter per second squared, right? Newton is kilogram meter per second squared. And they have a second as well. So second cancel with 1 second here. So you figure out the unit for impulse in terms of the basic unit is kilogram meter per second. 1 second cancels. What's my point? Remember the unit for momentum? It is also kilogram meter per second. Same. So this is an important point, okay? Impulse and momentum has the same unit. This must be ringing a bell for you. In chapter 5, something similar happened. We defined the kinetic energy. We said the unit is joule. Then we defined the work done by a constant force. The unit also joule. Something similar happening here. We define the momentum. Its unit is kilogram meter per second. Now we define the impulse. Its unit is kilogram meter per second. So impulse and momentum has the same unit. Good. All right. So just remember that. Now, like we did in chapter 5, what did we say? Work done is the change in the kinetic energy. Exactly the same way, impulse is the change in the potential, not potential, momentum. Change in the momentum. Something very similar. Okay, so there is an analogy between that and this. Okay, so kinetic energy here, momentum. Work done here, impulse. So this is called impulse momentum theorem. We can prove it very easily. So we define the I, which is force into delta t. We define the momentum, which is mass into velocity. These are definitions. Then we say these two are related simply like that. Impulse is equal to change in the momentum. It's a very powerful formula. I can prove it starting from the Newton's second law. I mean, put it in this way. The net force is equal to delta P over delta T. Then you can bring it to this way. Then F delta T is equal to delta P. Now we call this what? We call this I. That's the definition of I. So here we have, instead of I have the F delta T. So it just proved very quickly. So it all follows from the Newton's second law. F times delta T is equal to I. That is the definition of I. If you have a force which act on an object for a time period of delta t, the product of force and the duration is called the impulse. So I is equal to F into delta t, not F. Why? You look puzzled.
I'm trying to.
Okay. Now, here, I mean, there is nothing so far to anything to deeply understand. I have a definition of something called F delta t. We want to call it impulse. Okay. So it is not just the force multiplied by how long the force is acting on the object. So it is something more than just the force, right? So impulse. So impulse, to get a feeling of impulse. So suppose you apply a force on an object, say for only 1 second, it will have a certain impulse. If you apply the same force for 2 seconds, the impulse will be more. So depending on the impulse, the change in the momentum will also be changing. If the impulse is less, the change in the momentum will be less for the same force. If we apply the same force for a longer period, it will be a greater impulse. So the change in the momentum will also be greater. So this concept of impulse has a deep meaning. Okay, it is very useful. So that's why we want to call this guy not just the F, not just the delta t, the product of them as impulse. Good, right. It's good to ask question, but sometimes then we get delayed. So I'm recording this, so you can also listen to this later, right? Right. So now the definition of impulse for a constant force, right? But usually the force is not constant. Like hitting a ball with a bat. So the force on this ball, it's not a constant force. When it is about to touch the ball, it will start with 0 because not yet touching. The force on the ball is 0. So then it will be like a pulse, right? At maybe t equal to 0 here. This is the time. It will start from 0 and it will rapidly increase and come to a maximum value, something like thousands or 10,000 Newton. It's a big force, right? We hit it, smash it. So it will rapidly rise to a certain big value. Then as the ball is leaving, it will gradually, very sharply drop to 0. When it is leaving, there will be no more force on the ball. So it is something like a pulse. Okay, it's a varying force. It is not a constant force. But this definition of I that we have, it assumes it's a constant force. So multiply by the time duration. The time duration is maybe like 0.01 second. Okay, very like 10 millisecond. That's what the time duration we are talking about, right? So what do we do with this case? Now, if it is varying force, how do I get the impulse? It's easy. We have what we call in a differential calculus. We break it to small time. Okay, say maybe it is 0 to 10 millisecond. You take a small duration of say 0.001 second, or very tiny, mathematically small. So you can say in that small duration, it has a constant value. The force has a constant value, certain constant value. So I can say this area is F1 delta T1. Then you go to the next area. So here the force is again another constant, F2. So this will be delta T2. So you can break this into smaller and smaller part. And this is the area, right? F1 delta T2 mean this area, because this is F and this is delta T1. So you take this area. Then you take the next area. This is F2 delta T2. So you can cover the whole thing with these small strips. That means, in other words, the impulse will be the total area under the curve of force versus the time. So for a varying force also, you can say the impulse is equal to sum of all these small areas. That means at the end it will be the area under this curve. So if someone gives you the force against the time curve, by getting the area under the curve, we can get the impulse. But don't worry, you are not going to calculate the area. You can calculate the area if you know integration, but it is not out of the scope of this. So we will do another trick. What is that? Say this is the actual force. It varies with time. This is the actual force. It varies with time. And the impulse will be the area under this curve. Good. We will introduce the average value for this force. This is the varying force. So we will introduce, let's take an average value, which is a constant value from the same initial time to the same final time, such that area under this constant force, the blue shaded area, is equal to the area under the actual force. So you choose a value of an average value for this force, which is not a constant. So we get an average value such that the area under this average force, the blue area, is equal to the area of the actual force. So that's how we get the average value for this force. Now again, you do not have to, because I'm just explaining the concept, right? You don't have to worry about how to find the average force. No, don't worry, okay? I'm just explaining the concept. So what we will say now, even if the force is varying, the impulse is equal to the average force multiplied by delta t. So we get an equation for even for a varying force. Simply we replace the force by the average force, which will give the same impulse as with the actual force. The average force can be thought of as the constant force that would give the same impulse to the object in the time interval as the actual time varying force gives in the interval. Right. Now we are ready to solve a question involving what we learned so far. What did we learn? We defined the momentum, then we defined the impulse, then we said we have a theorem or a law, we don't call it law. The impulse is equal to change in the momentum. This is after defining both of them. What is the definition of momentum? M into V. What is the definition of impulse? F average, because the force can be not a constant force all the time. So F average multiplied by delta t. These are the definition equation. Then we say these two are related. So this we have a theorem which tells you impulse is equal to change in the momentum. Now what is this question? We are going to apply what we learned now. The question is, we have a golf ball, very small, light mass, is about 50 grams, so 5.0 10 to the minus 2 kilogram mean 50 gram, but SI unit is kilogram, and it is stuck with a club. Initially the ball is at rest, you know how it is played, right? The ball is at rest, and someone come, use this, what you call the club, and hit the ball with the club. So the ball's momentum will change. What is its momentum initially? 0. When you hit, it says it gains a velocity of 44. This is the final velocity. So the initial velocity, therefore the initial momentum is given, because mass is given. So mass into velocity will be the momentum. And the final velocity and the mass is also there. So we also know the final momentum. So in the question, initial momentum is given, final momentum is given. Then what is the first question is, find the magnitude of the impulse. We are asked to find the impulse. So how can I find it? First thing, you have to go for the definition, right? That is a natural thing to do. Whenever a question is asked, so like kinetic energy, what is the kinetic energy? You go for the definition. Definition of the impulse is, if it is a non-constant force, the average value of the force multiplied by the duration of the force. Do I know this? Is it given in the question anywhere? No. Do I know this? That's also not given in the question. Yeah. Yes. So, but you have to go step by step. First thing to go for the definition. If the definition doesn't help, see if you have any theorem or law. Yes, we have this guy. The impulse is equal to change the momentum, and we can know this because everything is there in the question. So the impulse, the change of momentum will be mv final, that is the final momentum, subtract mv initial. This is the initial momentum. These are all given. So all you have to do is to substitute. Come to the front, please. Come to the front. Come to the front. Excuse me. Yeah. Guys, just come just for the attendance, huh? So substitute the values. Mass is this. Final velocity is this. What is the initial velocity? It is kept at 0. So you will do that, then you will get this answer. Okay, I will not do the substitution. You please check that. So everything is there. So see how it went, right? You are asked to find the impulse. You look for the definition of the impulse, but it is not going to help us because we don't know what the average force is. We don't know what the duration of the force. So we give it up and go to the theorem. And from the theorem, because the initial momentum and the final momentums are given, you can use that equation to find the impulse. Now B, question B. Yeah, now he is asking to find the delta T and the average force. The delta T can be found because we have got some extra information, which is, stand up please, come to the front now. Excuse me, stand up please. Come and sit in the front please. You're just smiling and talking to each other. Take that chair and put it properly and sit there. So how do I do this? There is some extra information here. He's saying while the ball is in contact with the bat, it is moving without leaving the thing because it will get compressed and it will stay with that for the time is not there. That is what we are asked to find. But the displacement is there. So we can say, if I make a box here to get the time, so we have the initial velocity 0, the final velocity 44, and the displacement delta x is 2 centimeters. That's an important information. So 0.02. So we have the initial velocity, the final velocity, and the displacement. Now we are going to assume it is a constant acceleration. While the ball is in touch with the club and it is being compressed, and there will be some motion before it leaves the bat, the club. And we will say it has a constant acceleration, then we know I can find the time, even the acceleration. 3 things are given to us, only 2 unknowns, and if I assume it's a constant acceleration, I can find the time. So it's chapter 2. You're going back to chapter 2. So go and pick the equation which doesn't have the acceleration, because I am not interested in finding the acceleration. So that is this equation. Delta x is equal to half initial velocity plus the final velocity into time. So we know this, we know this, we know this, only unknown is time. So I can calculate the time. You will get this answer. I will not show the substitution, so please substitute. And yeah, you have a question?
This formula is the formula sheet of
Yeah, you had, I mean, if it is needed, I will put it in the formula sheet or even in the question itself. Remember, in midterm 2, although it is not part of chapter 4 and chapter 5, you have the equations of motion, right? So, I mean, midterm 3, I will do the same thing. Suppose it is needed, I don't want you to memorize these things, so it will be in the formula sheet if needed. Okay. So this is not an exam question. This is like a homework question, example question. So that is why it is long. So don't worry unnecessary. So let me go to the B. So we got this, right? Now the next is to find the average force. Now you go to this equation, which tells you impulse is equal to the average force multiplied by delta t. We found the delta t now, right? And we found I from part A. So average force will be equal to I divided by delta t. I from part A, we have the answer A, 2.2 kilogram SI unit. Delta t we found here just now, 9.1 10 to the minus 4. So you will get this answer. Okay. All right. So we solved the question as well. Let me go to the next. Sorry. Okay. Sorry. Yeah. Excuse me? What's so funny? So please listen. Happy. Oh, okay. Right. Momentum. And this is one dimensional, right? Because you hit the ball, the velocity is 0 for the club and velocity is 0 for the ball. Just after hitting, the club is not going right after hitting, okay? The club is in, in the same place, and this guy has some velocity, so that's what you want to find. So it's a one-dimensional problem. Everything is to the right, okay? One-dimensional problem. Okay. Now we have an important application of what we learn in everyday life, auto collision. In vehicle, road accident, you can have crash or collision. So one of the important factor in the collision is the collision time, the duration of the force. So when imagine two cars are hitting each other, how much time it took for the momentum from a very big value, it will come to a 0, right? It will be stuck because of the collision. So the duration of that collision is an important factor. Why? Look at our equation. The average force is equal to change in the momentum divided by the duration. So that's our equation. If the change in the momentum is big, the force will be big. Suppose you have a car which is moving at a speed of 100 kilometers per hour, then because of the collision, it comes to 0 velocity. So there's a very big momentum change. That means the force will be also big. If delta P is big, the force will be big. Now what about the delta T? It is in the denominator. If the time is big, it is good. Because when you divide something by big number, it will be small. So if the delta T is big, we are happy because the force will be small because it is in the denominator. So this delta T is an important factor in a collision. We try to make it as big as possible. How do we do that? With seat belt. with airbags. Both of them help to make the time big. Let me explain how. So suppose a car is coming with 100 kilometers per hour, then it will be stopped by hitting another car to come to zero, maybe in 0.1 second. The car will be stopped maybe even less, 0.01 second. Typical value will be like 10 milliseconds. The car will be stopped. But you, the passengers inside the car, especially the driver, everyone's supposed to wear the seat belt, right? So seat belt will do what? It will increase the time. If the seat belt is not there, you will go and hit the steering wheel and you will be stopped. Okay, it may be a little longer than the car itself because you are moving forward before you stopped, but still it will be like 0.01 second, about 10 milliseconds. Let's say take a typical data. You are the passenger inside the car, your mass is 75 kilograms, and you are driving at a speed of say 60 miles per hour, it is roughly 80 kilometers per hour. No, I think 60 will be 80 kilo. I don't know. Let's say something close, 80 kilometers per hour. Multiply by 3.6, you will get the value. So it's 27 meter per second in SI unit. And typical value is you will come to zero by hitting the steering wheel in about 10 milliseconds, 0.01. This is a typical data, okay, actual data, average value. So let us calculate the force on you because of that being stopped. Delta P divided by delta T. Mass, final velocity minus initial velocity. Final velocity is 0, initial velocity is 27, and mass is given 75, divide by the time, which is 0.01. If you put the value, you get this value. Very big, 200,000 Newton. That can kill someone. Okay, the force is so great. 200,000 Newton, it can kill someone. You know why negative value? Because you choose the velocity to be positive, say to the right, and the force on you will be in the opposite direction. That's why the negative. So you can just say magnitude will be 200,000 Newton on you in the opposite direction of the direction the car is moving. So this force is 200,000 is too much actually. If you get the acceleration, it will be, the acceleration will be 280 divided by the mass, multiply by 9.8. So in terms of the gravitational acceleration, it's 280 times the gravitational acceleration. It's a huge acceleration. The force corresponds to 200,000 Newton. It's really indeed a big force. It can kill. It is fatal. You know the meaning of fatal, right? Fatal, deadly. Right. So seat belt, what it does is to increase the time from 0.01, so 10 millisecond to 150 millisecond. If I now use this new time of 150 millisecond and calculate the force with the new time, before you divide by 0.01, now you are dividing by 0.15 second. With the same value on the top, you get the force to be 9,800 Newton, 9.8 kilonewton, which translate to 9,800 Newton. Please put your phone away. Put it down, please, face down, yeah, and pay attention here. So the average force is 9,800. That's a great reduction, okay? 1 order of magnitude less. So that shows you how seatbelt can help to reduce the damage. What happened with the airbag? It can even further reduce the collision, increase the collision time, therefore decreasing the force, average force. So, you know, hit the airbag, so you'll be coming to zero velocity. It will take even longer time, okay? And also it has further advantage, because the airbag, it will cover a big area, right? So you're not hitting like the steering wheel, you are hitting so you'll be cushioned. I mean, the force will be spread over big area. So the pressure on you will be less. So you will not have penetration wounds, right? So if you hit the steering wheel, which is a small area, So it can damage you more. The pressure on your chest area will be larger. So it can damage more because the force is not spread over big area. So the force that you experience will be greater in any one point. So now we come to the conservation of momentum principle. Like we know that energy is conserved in an isolated system. Momentum, what we define, is also conserved in an isolated system. What is an isolated system? What is an isolated system? Anyone can tell me?
There is no thing.
Nothing coming from outside. It is completely isolated. Isolated, what is isolated? So in other words, no external force, okay? All the forces are all internal forces. So if there is an external work, energy can go in, come out. So no external force, they cannot do any work. So such a system, we can show the momentum is conserved. So we will look at an isolated system and we will apply the conservation of momentum principle. But let me first show you or prove that for isolated system, we will have conservation of momentum. Now let me state the conservation of momentum principle again. Could you please sit down? Please sit down. Nobody is leaving, I took the attendance and now you want to leave. No problem, please stay till I finish, okay? Principle of conservation of momentum state that when no external force acting on a system consists of, for example, two objects that are colliding with each other, it can be more than two objects. So imagine such a closed system, isolated system, then the total momentum of the system remain constant without changing in time. As the time goes by, anything happen, they might be colliding with each other. But if you calculate the total momentum at any given time, it will be equal to the total momentum sometimes after. Right. So we will look at a specific example of two objects. One is a blue ball with a mass m1 and having a velocity v1I. The 1 is for the ball 1 and I for initial, before collision. And for the ball m2, it is v2I, 2 for the ball 2 and I for the initial. This is before collision, then because they are coming towards each other, they are going to collide and their momentum will change. The ball m1 will have a new velocity, v1f. It changed from v1I to v1f. And this orange ball will have a new velocity. It will change from v2I to v2f. So that means their momentums are changing. But however, the total momentum before, this is the conservation of momentum, is equal to total momentum after. You know what this means? You are adding the momentum, sum of the momentum before. So in other words, if you have two objects, P1 initial plus P2 initial, add them, equal to P1 final plus P2 final. So this is the conservation of momentum. And if you want, you can go further. So P, I can write mass into the definition of momentum, V1I plus mass M1, M2 into V2I, that is the left-hand side, the total momentum. On the right-hand side, M1 V1F plus M2 V2F. So, everything going to be in the same x-axis. So it's a one-dimensional problem, but you need to take care of the vectors. So if you choose the right side to be positive, so the V1I you can see it is positive. So you will write a positive number here. And if you look at for this particular example, not always, V2I is to the left, so you will write a negative number here, and so on. So that we need to take care of. Okay, so you make sure that you put the signs correctly because it's a vector equation. All right. Now we are going to prove this conservation of momentum by bringing in the Newton's third law. So we were looking at this example of a blue ball which is moving to the right, and the red ball or the orange ball, whatever, moving to the left. And when they hit, there will be force on the red ball, it will be to the right, and there will be a force on the blue ball, which will be to the left. And I'm going to plot the forces as they're making the collision versus the time, the force versus time. So for the red ball, it will have, before it hits, it will have a 0 force, and maybe at 1 second, it may have, say, let's say 10 Newton to the right direction, so positive force. Then according to Newton's third law, the blue ball at the same instant will have a force with the same magnitude, but in the different direction, in the negative direction. So this happened throughout, right? So every time, say 2 seconds, it will be here, say 15 Newton. And for this guy, it will be negative 15 Newton. So, and so on. So the red curve will be exactly the mirror reflection of the blue curve. Yeah, in the opposite direction. All right, so I can say the impulse for the red ball is this area. So that is what we said before, right? If it's a varying force, we can still find the impulse, excuse me. The impulse will be the area under the curve. So we call it I1. And for the blue ball, the impulse will be this area. So say this is I2. Now you know the area are equal. Newton's third law. So that means also equal but opposite in sign. That means I1 plus I2 will be equal to 0. Okay, fine. Then I know the impulse momentum theory. I can so the impulse is equal to change in the momentum. So instead of I1, you can put delta P1. So I1 is delta P1, I2 is delta P2. So you substitute that value, so you get delta P1 plus delta P2 is equal to 0. That means, suppose for this is the blue ball, say there's a change, after collision it changes its momentum, right? The velocity changes mean the momentum change. So maybe 10 units of increase, let's say. Yeah, that means the other ball has lost 10. So the total change is 0. Thank you. So that means total momentum is not changing. You can take the delta out. So the P1 plus P2 is the total momentum. So there is no change in the total momentum. So it might exchange the momentum. The ball 1 will lose some momentum. It will go to the ball 2. Okay, vice versa. So this can exchange will happen, but the total momentum will not change if it is an isolated system. So we have proved it now. So we saw that before, right? This expression, I showed it to you. When you have two balls that are colliding, if it is an isolated system, I can write this. M1V1I, it's a vector equation, that's what you have to remember. Now we are assuming there are no external force, so the only internal force because of an isolated system. So we can now do this question where we have an astronaut, someone in the space, okay, there he comes in a shuttle, spaceship or shuttle, and this guy comes out of the spaceship, and there is a rock or satellite which has a mass of 350 kilogram. The astronaut, she's called Anne. She has a mass of 60 kilogram. So we know the mass of the astronaut, and we also know the mass of the satellite. So they are here. Yeah. Oh yeah, I come to that. Right. So they are at rest, right? So there is a tether, like a cable or something. Usually that's the case. Can you walk on the space? Is it possible to walk? No, you cannot walk. In the floor, how do you walk? You push the floor back, and the flow push you forward. That's how you walk, right? But in the space, there is nothing, no flow, no flow. If you're in the water, how do you move? By pushing the water back. But in the air, you can probably do it, but it will not be that much of a force. But in the vacuum, in space, there is not even air. So unless you have a rope or something connecting to the ship, you cannot get back to the ship, right? Unless you are connected by something. Suppose it's broken. That's it. You are in the space unless the ship come closer and pick him up. But you can do something. Suppose there is some rock or something in the space, you are close to it. You can push it. When you push it, what happens? The rock will push you in the opposite direction. Say you can take this and you throw this. When you throw this, you have to apply a force. So this will apply a force on your hand, push you back. But how can I do it here? That force will be very, very small, right? Yeah, 10 Newton, whatever. So the friction from the flow will stop me. That force is not enough. Also, there's yeah, Newton's third law. When you apply a force on this one will push me back. But that force will be very small. It can stop my foot, and the floor has a friction force, which we will not go anywhere. But in the space, there is no air resistance, there is no flow. You're welcome. So, right. So here, you push this, and this guy will experience a force, so he will move backward. But we solve this. You solve this problem by applying the conservation momentum. This is a very nice way of doing this. Initial total momentum is equal to final total momentum. This is what we are going to apply. So initially, we have the satellite initial plus and the astronaut initial. They are both zero, right? Initially, they are at rest. Is equal to momentum satellite final plus P astronaut final. This is zero because the velocity is zero. This is also zero because the velocity is zero. Then the astronaut giving a velocity to the satellite by pushing it to the left. Okay, so we can say mass of the satellite multiplied by the speed of the satellite, but it is, since I have chosen the right side to be the positive side, and this will be the negative velocity, so minus 0.90 plus, and this one will be mass of the astronaut multiplied by the velocity of the astronaut finally after collision. All right, we don't know that. We know the mass, we know the ms, we also know ma. Look at this. How many unknown? Only the astronaut velocity. So substitute everything else, but with the sign, right? For example, velocity here is minus. So you will get the velocity of the astronaut to be plus. Because this goes to that side, it will become plus. So velocity of the astronaut will have some value. Please calculate it, and it will be a positive value. What is that? Yeah, you got the answer. Please, somebody check the answer. He says 5.25 meter per second. Please check that. I am not sure. So Nawaf is responsible if it is wrong. Okay. Right. Please check. Yeah. Thank you. No. Yeah, but I put this to be negative. So this will be in the opposite direction, so it will be positive. You will get a positive answer because this goes to the other side, it becomes positive.